Unit 5.5 is concurrent lines. Concurrent lines. There's four things we're going to talk about that are concurrent. First of all, we need to define concurrent. Concurrent lines are lines that all intersect in a point. They all intersect in a point. Now, again, there's four things we're going to talk about that do that. The angle bisectors, the perpendicular bisectors of the sides, the altitudes, and the median. We've defined what those things are, but we haven't talked about what happens when you draw all of them within one triangle. And so that's the lesson for today. So Theorem 5.8, the bisectors of the angles of a triangle all intersect at a point. Now, that intersecting at a point means that they're concurrent lines. Okay, when you draw the bisectors of the angles of a triangle, they intersect at a point. Or we could say that they are concurrent such that they are equidistant from the three sides of the triangle. So let's look at the picture here. When we talk about the angle bisectors, the bisector of angle E, that big angle E, whoa, looks like that's a little wiggly there. Let's try that again. That would keep going, you see, the bisector of the angle. And then the bisector of angle G would do something like this, and it would keep going. And the bisector of angle F, let's finish the little marks with G. There's showing that angle G got bisected into the two little angles. And angle F was bisected by this ray. And you can see that they intersect at a point, or we could say that they are concurrent at a point. The bisectors of the angles of a triangle are concurrent at a point such that that point is equidistant from the sides. Now, we've already defined the distance from a point to a line. The distance from that point of concurrency to this side is defined to be the length of the perpendicular segment drawn from the point to the line. So, segment AD is the distance from the point to side EG. The distance from that point to side LP is the perpendicular segment drawn to it, which would be segment AB. And the distance from the point of concurrency to side FG would be segment AC. So AB is equal to AC is equal to AD. That point is equidistant from the sides. The bisectors of the angles of a triangle are equidistant from the three sides of the triangle. We call this the end center. Point A would be called the end center. It is called the end center because it is the center of a circle that could be inscribed. If we used that point of concurrency A as the center and one of those distances like AD as the radius, and we opened it up with a compass, then we could actually inscribe a circle inside the triangle. It is inscribed. Therefore, we call the center of it the end center. Now, the word scribe means to write or to draw, and inscribe then would be to draw inside. So we drew a circle inside the triangle, or we inscribed it. We call that point the end center because it is the center of the inscribed circle. Okay? The bisectors of the angles of a triangle intersect at a point equidistant from the three sides of the triangle. That point we call a point of concurrency. We say the lines are concurrent because they hit at a point. That special point for the angle bisectors is called the incenter because it is the center of the inscribed circle. Okay? Theorem 5.9. Theorem 5.9, the perpendicular bisectors of the sides of a triangle intersect at a point, which means that they are concurrent at a point, equidistant from the three vertices of the triangle. So here's what we're thinking here. We're starting out with side QR. We want something that bisects it, which means that F is the midpoint, and it makes QF equal to FR, but it's also perpendicular, and you can just keep drawing that perpendicular line. It hits at 90, see? And then if we had side HR, and we found its midpoint Z, meaning that HZ is equal to RZ, and we drew a perpendicular, which means it hits at 90, then we've got the perpendicular bisector of HR. And then we have this side HQ, whose midpoint is Y, meaning that HY is equal to YQ. And then we're going to draw a perpendicular from that point. Then we have the three perpendicular bisectors, and I got a little off there, but they should have been concurrent at that point. The perpendicular bisectors of the sides of a triangle intersect at a point, meaning they are concurrent at a point that is equidistant from the three vertices. Now, the distance that that point is from the vertex Q is segment XQ. The distance that the point of concurrency X is from vertex H would be segment XH, and then again segment XR. So the conclusion is that point X, the point of concurrency, is equidistant from the vertices Q, H, and R. Therefore, segment XQ is equal to segment XH, which is equal to segment XR. If we used X as the center, and one of those as a radius, and we used our compass, then we could circumscribe a circle about that triangle. Notice every vertex of the triangle touches the circle. Because we drew a circle around, draw we call scribe. A round is the circumference, right? And so we would say that we circumscribed. We drew around the circle, circumference. We drew scribe around the circle, circumscribe. And therefore we call the center of that the circumcenter. So the perpendicular bisectors of the sides of a triangle intersect at a point that is equidistant from the three vertices of the triangle, or they are concurrent at a point equidistant from the three vertices. That point of concurrency is known as the circumcenter. If you use that and one of those distances as the radius, then we could circumscribe a circle about a triangle. Okay? So we've talked about the concurrency of the angle bisectors. We talked about the concurrency of the perpendicular bisectors of the sides. Now we're going to talk about the concurrency of the medians. Remember that a median of a triangle is a segment from a vertex to the midpoint of the opposite side. The medians of a triangle intersect at a point, which means that they are concurrent. That makes one piece twice as large as the other piece. Now, that's a shortcut method of saying a fancier theorem, and I'll say it correctly in just a minute. I wrote it this way in the book just so you can understand that that median gets hit with that point so that one of the pieces is 2/3 of the whole median and the other little piece is 1/3 of the whole median, which you could see that they're in the ratio of 2 to 1. Long piece to short piece is in the ratio of 2 to 1. So you could think of things like 2x plus 1x when you think about page 52 of the algebra book. To assign variables to things in a ratio, you would multiply each member of the ratio by x. So using algebraic lingo, we could say if this is 2x, then this would be 1x. They're in the ratio of 2 to 1 for any integer value that you plug in, or any real number that you plug in. Okay. So the medians of a triangle intersect at a point. Now, this is the way it's more properly written in a formal definition. The medians of a triangle intersect at a point that is 2/3. In other words, this point is 2/3 of the distance from the vertex. So if we go from the vertex to the midpoint of the opposite side, that's what a median is. It's a segment from a vertex to the midpoint. Well, it's saying that the point where they hit is 2/3 of the way from the vertex to the midpoint, meaning that the part on the vertex end is the big part, and the part on the midpoint end is the little. Okay? So formal definition, the medians of a triangle intersect at a point that is 2/3 of the distance from the vertex to the midpoint of the opposite side. What we see out of it is that it's divided such that one piece is 2/3 and one piece is 1/3. They're in the ratio of 2 to 1. It's going to be pretty obvious when you look with your eyes which one's the big one and which one's the little one. But the big one is on the vertex end and the little one's on the midpoint end. Hence the concept 2/3 of the distance from the vertex to the midpoint of the opposite side. Okay, so let's look at this again. If we wanted to draw a median from X to FQ, we would find the midpoint of FQ, and we would draw from the vertex to that midpoint, and that would be that median. If we wanted to draw the median from Q to the opposite side, XF, we would find the midpoint of XF, which is A, and we would draw from the vertex to that midpoint, and that would be the median from Q to FX. If we wanted to draw the median from point F to side, I'm off there, to side XQ, then we would find the midpoint of XQ and draw from the vertex to the midpoint. You can see that those medians were concurrent at a certain point, point E. And if we drew it exact and we measured, which you may have done in the discovery work, then you would see that they're in a ratio of 2 to 1. This blue piece is twice as big as that blue piece. They're in the ratio of 2 to 1. This green piece, which we'll call 2y, is twice as big as that one, which we could call y, etc. So, looking at that, and I'll get that out of the way so we can see the letters, we can say that XE we can say that XE, I lost my ability to write there. Let me make a couple of clicks so my pens will come alive again. The big piece of this median XE is twice as big as the little piece XI. So XE is equal to 2 XIs. XE is equal to 2 XIs. Excuse me, I'm going to pause a second and fix everything again. Okay, so let's look at this again. Maybe things will stay put a little better for me. There we go. We're on track. So the big piece here, XE, is twice the little piece, XI. There we go. Very nice. The big piece here, QE, is twice the little piece, EA. QE is twice EA. The big piece, FE, excuse me, is twice the little piece, EB. So the medians intersect at a point such that the big piece of each median is twice the little piece of each median, or in other words, in a ratio of 2 to 1, or formally, that point is 2/3 of the distance from the vertex to the midpoint of the opposite side. Now, mean, median, and mode are words that we're familiar with from algebra, and on page 66 of my Algebra 1 textbook, the title of that lesson is Measures of Central Tendency. So when we think about median, we're thinking about a measure of central tendency. The median actually hits at the midpoint, which is the point in the center of a side. And so they gave this point of concurrency the name centroid, after the fact that a median hits the midpoint, or it's a center, or a median is a measure of central tendency. So we call that the centroid of the triangle. Okay? So we've come up with an incenter, a circumcenter, and now a centroid. As we continue to make conclusions here, we can say that XE, the big one, is twice the little one, or we could say that XE is 2/3 of the whole thing, XI. Which says I made a mistake here, and I apologize for that. The big piece, XE, excuse me, is twice the little piece, EI. I wrote that down wrong. I had to correct my board in the middle of it, and I kind of got off, I guess. That's just an excuse, I'm sure. QE is twice the little piece, EA, but it's 2/3 of the whole thing, QA. FE is twice the little piece, EB, but it's 2/3 of the whole thing, FB. And I'm off again. Any questions on the centroid? Okay. So the bisectors of the angles of a triangle intersect at a point equidistant from the sides of the triangle. So we could draw the angle bisectors and find the incenter and inscribe a circle in the triangle. The perpendicular bisectors of the sides of a triangle intersect at a point equidistant from the vertices. So we could draw the perpendicular bisectors of the sides and find a point known as the circumcenter, and we could circumscribe a circle about a triangle. The medians of a triangle intersect at a point 2/3 of the distance from a vertex to the midpoint of the opposite side, which to us says there's going to be a big piece and a little piece, such that the big piece is twice the little piece, or the big piece is 2/3 of the whole thing and the little piece is 1/3 of the whole thing. That point where the medians intersect is called the centroid, and we don't do any fancy circle drawing with it. Okay? All right. There's one other, and we didn't talk about it, but if we go back to Unit 5.4, we talked about the altitudes, and we defined an altitude as being a segment from a vertex perpendicular to the line that contained the opposite sides. The altitudes are also concurrent, and that point of concurrency when you draw the altitudes is called the orthocenter. We didn't discuss that in this text. I just was going to make you aware of that. Okay, so daily work, Unit 5.5. Name 3 equal segments and tell why they're equal. Well, what we're given is angle bisectors. And so what we have here is that AG is an angle bisector, CG is an angle bisector, EG is an angle bisector. The bisectors of the angles of a triangle intersect at a point that is equidistant from the sides of the triangle. Intersect at a point that is equidistant from the sides. So this distance is equal to this distance is equal to this distance. So we conclude that BG or GB, if we go from the center, is equal to GC, which is equal to, I'm sorry, I messed up. GB, excuse me, is equal to GD, which is equal to GF. And the reason is the bisectors of the angles of a triangle, we're going to abbreviate bisectors of angles of triangle are equidistant from the sides of the triangle. We kind of abbreviated a lot. The bisectors of the angles of a triangle are equidistant from the sides of the triangle. That point, and you didn't have to say this, but that point is called the circumcenter. And if we use that circumcenter with, I'm sorry, that point is called the incenter. I'm trying to mess up. That point is called the incenter. And if we use that incenter and one of those distances as a radius, then we could inscribe a circle inside of that triangle. We'll talk later about that each side would be tangent to the circle, and B, D, and F would be points of tangency, but that's further down the line study. Okay? All right? This looks kind of like a crazy mess, doesn't it? Now, the first thing we need to kind of see here is that the original triangle was triangle UQS. Triangle UQS. So what's been drawn here? What's been drawn is the perpendicular bisectors of the sides. P is the midpoint of this side. And so TR is the perpendicular bisector of that side. Y is the midpoint of this side. So YR is the perpendicular bisector of side QU. X is the midpoint of this side. Excuse me, I'm trying to hit stuff and I'm off again. I'm having trouble keeping things oriented here. And so UR is the perpendicular bisector of that side. Now notice that the point of concurrency is not even in the original triangle. When we drew the perpendicular bisectors of the sides, they are concurrent at a point. That doesn't necessarily have to be in the triangle. But the thing says that the perpendicular bisectors of the sides of a triangle intersect at a point that is equidistant from the vertices. So from R to this vertex, which is RU, R to this vertex, RS, and R to this vertex, RQ, are all the same. So RU is equal to RU is equal to RS because, and we'll abbreviate again, perpendicular bisectors of the sides of a triangle intersect at a point equidistant from the vertices of the triangle. That's about as short as we can try to abbreviate it. The perpendicular bisectors of the sides of a triangle intersect at a point that is equidistant from the vertices of the triangle. Now, if we used that point currency as the center of a circle, and we used one of those segments as a radius, then we could circumscribe a circle. That got ugly. I didn't stay round, but anyway, we could circumscribe a circle about that triangle. I didn't do a very good job of making a perfect circle, but you get the idea, okay? The perpendicular bisectors of the sides of a triangle intersect at a point that is equidistant from the three vertices of the triangle. So we would say that the circle is circumscribed about the triangle. We could say that the triangle is inscribed in the circle, okay? All right, next picture. What's drawn here are the medians. What's drawn here are the medians. Okay, number 3, AX. What's drawn here is the medians. If I were to go from this vertex, F is the midpoint of the opposite side. A segment from a vertex to the midpoint of the opposite side is called a median. From point P to the midpoint of the opposite side, point E, is a median. From I to the midpoint of the opposite side, B, is a median. The medians of a triangle intersect at a point, meaning that they are concurrent. That is 2/3 of the distance from the midpoint to, from the vertex to the midpoint of the opposite side, meaning that it makes one piece 2/3 of the other piece. The big piece is 2/3 of the little piece. Or the big piece is twice the little piece. They're in the ratio of 2 to 1. So if this big piece is 6, then the little piece is half of that 3. If this little piece is 2, then the big piece is twice that 4. If this little piece is 3.5, then the big piece is, well, it just kind of dawned on me. I've been on a roll and I've done every one of these, and this is your homework. So we're going to let you finish that. That way you get to do a little bit on your own. Okay, so you can go from there. All right. We've got AX is 4 in blue there. We'll go ahead and fill that in. We've got XE is 3. we'll go ahead and fill that in, and we'll let you mess with the other. Okay? All right? The next picture has medians also. And so it says IH is 4 3/4. That's the whole median from here to here. We know that the medians intersect at a point that is 2/3 of the distance from a vertex to the midpoint of the opposite side. In other words, the big piece IR is 2/3 of the whole thing, and the little piece RH is 2/3 of the whole thing. So IR is equal to 2/3 of the whole thing, IH, which is 4 3/4. So we need to take 2/3 of 4 3/4. Well, we learned in the Algebra 1 book on page 5 that to multiply, you multiply the numbers and you multiply the names and you get a new name. And then we progressed and eventually we multiplied mixed numerals on around page 11 or 12 in the Algebra 1 text. But here's the way we taught it. We said the numbers are on top. The fancy word is numerator. The names are on the bottom. The fancy word is denominator. We're going to have to change this 4 3/4 to an improper fraction. So we go 4 times 4 is 16 plus 3 is 19 of those little fourths. That's in the Algebra 1 textbook around page 10, 11, 12, right in there. Okay. So then what we said is you're going to multiply the numbers and you multiply the names and you get a new name. Multiply the numerators, multiply the denominators. But before you multiply the numerators, multiply the denominators, you know that we could cross reduce. So let's go back to what we had. 4 times 4 is 16 plus 3 is 19 of those little fourths. So now we know we could cross reduce. 2 goes into 2 once, 2 goes into 4 twice. And then you multiply the numbers 19 and you multiply the names and you get a new name 6. Multiply the numerators, multiply the denominators. If you want a mixed numeral, you would do what it says. 19 divided by, looks like that, 6. 6 goes into 19 3 times. You multiply and you get 18 with 1 left over. If you want a mixed numeral, you put your remainder over your divisor. And so we get 3 1/6 inches for IR. Now, RH is half of that. RH, excuse me, is half of that. Well, how do you take half of 3 1/6? Half of means times 3 1/6. RH is a little piece. It is 1/2 of the big piece, so it is 1/2 of 3 1/6. Again, we need to make this improper. 3 times 6 is 18 plus 1 is 19 of those little sixths. 1/2 of that is the same as 1/2 times that. We're going to multiply the numbers 19, the numerators, and we multiply the names, denominators, and we get a new name. And then we're going to do what it says. 19 divided by, looks like that, 12. It'll go one time. You get 12, subtract 7 left over. You put your remainder 7 over your divisor 12. And we have 1 7/12. Now, I'm showing you how to do all of this on paper. I'm not showing you how to do it on the calculator because you need to know how to add, subtract, multiply, and divide fractions, decimals, and mixed numerals on paper. It's important when you're factoring. It's important when you're doing uh, college algebra, trig, and calculus. There's times you just need to know how to do these things on paper. So I encourage you to not just use fancy calculators to do it all, but to actually know the math involved. Now, we want you to know how to use the technology also, and I'm sure that you have already learned that and that you'll be instructed in that. And I would probably instruct my students on the side on that. But on these videos, I'm wanting you to actually learn how to do this on paper. And we will continue to do this on paper. Okay? And I encourage you as a teacher or as a student to get it done on paper also. Okay. Well, that is the end of that daily work, which gets us to the odd answer solutions. Don't forget the odd answers are not just in the back of the book, the solutions are. So it actually shows all of the work here. So again, don't forget that these are in the end of each chapter in the textbook. Okay. That's going to help you with some of this. Notice discovery, problem, solutions not given. But we know that in the discovery problems, the word part of the answer is the rule for the next page. So all you got to do is go to the next page and look at the theorems, and there's your answers. Okay. The numbers, as far as your measuring, is not there. You just got to do that. All right. Appreciate your attention.